Have you ever felt, I don't know, like you're just being pulled in a dozen different directions at once?
Oh, absolutely. All the time.
Right. Like you have work pulling you one way and family obligations tugging you another and personal goals dragging you somewhere else entirely.
Yeah, and it's exhausting.
It really is. And you just want to know where you're actually going to end up after all that pushing and pulling. Well, physics has an exact solution for that.
It sure does.
Today, we are doing a deep dive into this really fascinating slide deck presentation on the science of vector resolution.
Which sounds intimidating, I know, but it's really not.
No, it's actually incredible.
Yeah.
It's basically the mathematical engine behind how multiple chaotic forces combine into like one inevitable outcome. And for this mission today, I'm going to play the role of the enthusiastic student, and you're going to be the insightful tutor.
I love it. I am ready.
Awesome. So together, we're going to help you, the listener, figure out how to navigate these complex forces using two specific paths from our sources. We've got mathematics and we've got geometry.
Right. But before we get into the math or the drawing, we really need to establish a foundation.
Yeah, we have to make sure we're speaking the same language.
Yeah,
Literally.
exactly. I mean, to solve any complex problem, a student first has to learn the basic terminology.
So going through the first few slides here, they start by contrasting the customary or imperial units. So
Hmm.
that's your feet, your pounds, ounces, the stuff we use here in the US.
Right, the stuff that confuses the rest of the world.
Yeah, exactly. And it contrasts those with the SI system, which is meters, seconds, kelvins, kilograms, candelas, amperes.
Yes, the metric system.
But I mean, why does this matter so much? Like, why is this the very first thing we have to lock down?
Well, because physics relies entirely on the SI metric system to establish a single common language for the universe.
Okay, that makes sense.
If you don't have that, you get disastrous miscalculations. Like, remember the Mars Climate Orbiter back in the late 90s?
Oh man. Didn't that like crash or burn up or something?
It burned up in the Martian atmosphere, yeah. And all because one engineering team was using imperial units like pound force, and the other team was using metric newtons.
Oh wow. So it was literally just a translation error.
Exactly. It costs millions of dollars.
Yeah.
So, yeah, common language is crucial. Which brings us right into slide 3, describing reality through scalars and vectors.
Okay, let me push back slightly here because this is where it gets a little textbooky. If I'm driving, say, 60 miles per hour down the highway,
Uh-huh.
why does it matter if I call it a scalar or a vector? I mean, isn't speed just speed?
Well, speed is speed, yes, but 60 miles per hour is just a scalar.
Just scalar. Okay.
Because it only has magnitude. It's just a number, like
Hmm.
distance, mass, time, or, temperature. It just tells you how much.
Right, just an amount.
Exactly. But a vector, that gives you magnitude plus direction. So 60 miles per hour is a scalar. But 60 miles per hour north, that is a vector.
Oh, I see.
Yeah, and having that direction completely changes things when you're talking about displacement, velocity, acceleration, and most importantly for us today, force.
Okay, wait, I think I have an analogy for this to lock it in.
Let's hear it.
So, scalars are basically just the ingredients sitting in a bowl, right? But vectors are the specific instructions on how to actually stir them and bake them.
Oh, that's actually really good. Yeah, the ingredients are the magnitude, but without the instructions, the direction, you don't know what you're making.
Exactly. Okay, so now that we know what a vector is, how do we visualize it, like on a piece of paper, to actually solve a problem?
Well, that's where slide 4 comes in. We use an arrow.
Just a simple arrow. I love it. It translates all these complex physical forces into like standardized geometry.
Right. And there are 3 key anatomy parts to this arrow.
Okay, break it down.
First, the length of the arrow.
Hmm.
That represents the magnitude. A stronger force means you draw a longer arrow.
Makes sense. And then the angle of the arrow, like, usually measured as theta relative to a flat axis, that's the direction.
Exactly. And finally, the arrowhead itself, the tip, that points to this specific trajectory. It tells you which way it's going.
So we have our arrows. Now let's look at the ultimate challenge presented on slide 5,
This is where it gets fun.
if you say so. So I want you to imagine 3 forces pulling at the exact same time from the center of a graph, the origin.
Like a three-way tug of war.
Exactly. So vector A is pulling at 100 newtons, which is just a measure of force, and it's at a 37-degree angle.
Okay, up and to the right.
Right. Then the vector B is pulling at 100 newtons as well, but at a 150-degree angle.
So that's up and to the left.
Yeah. And then vector C is pulling at 80 newtons, a little weaker, at a 233-degree angle, down and to the left.
That is a very chaotic system.
It is. So the big question is, how do we find the net result when multiple forces act all at once.
Well, the slides offer two paths to figure this out. Path 1 is the component engine, which is all about mathematics.
Okay.
And path 2 is the graphical method, which is geometry based.
Well, let's start with path 1. Because I'm looking at this and I'm like, how can we possibly turn these diagonal competing forces into simple, clean math?
It seems impossible, right? But slide 6 has the secret. You realize that any diagonal vector is really just the sum of its horizontal and vertical components?
Let's break it down.
We use unit vectors, specifically I and j.
Oh, right. I and j, I remember this.
Yeah, so I is horizontal, j is vertical. They have a magnitude of exactly 1. They are basically the atomic building blocks of the Cartesian plane.
Okay, so we're turning the diagonals into right angles.
Yeah.
And I have to say, I absolutely love the metaphor they use on slide 7 for this.
The shadow metaphor. It's so helpful.
It really is. I'm going to take the lead on this one because I just love it so much.
Go for it.
So imagine you're shining a flashlight straight down from above one of these diagonal vectors.
Okay, shining straight down.
Right. It would cast a flat shadow onto the horizontal x-axis, right?
Right.
And then, if you took another flashlight and shined it from the side, horizontally across the page, it would cast a vertical shadow onto the y-axis.
Exactly. Those two shadows are your horizontal and vertical components.
It's so brilliant. But how do we find the actual length of those shadows?
Well, that's where a little bit of trigonometry comes in. We use the deconstruction math on slide 7.
Right, bring on the math.
So for vector A, which was 100 newtons at 37 degrees, we use cosine for the horizontal x-axis shadow.
Okay, let's unpack this.
So it's 100 times the cosine of 37 degrees, which gives us an x component of about 79.86 newtons. We tag that with I.
Right, because I means horizontal, and then for the vertical y-axis shadow, we use sine.
You got it. 100 times the sine of 37 degrees gives us a y component of 60.18 newtons tagged with j.
It is honestly just amazing how that works. We take one messy, confusing diagonal problem and turn it into two perfect perpendicular certainties.
It's incredibly clean. But we have to be careful when navigating the quadrants.
Right, slides 8 and 9, because vectors B and C are pointing into different areas of the graph.
Exactly. We do the same math for them, but we have to pay really close attention to negative signs depending on which quadrant they land in.
Yeah, like if a force is pulling to the left, the x component has to be negative, right?
Precisely. So after we do the trig for all three vectors, step 2 is just simple arithmetic. We accumulate them.
Tallying them all up.
Right. We add all the x-axis components together. And for this problem, the net x component ends up being negative 54.89 newtons I.
So overall, it's pulling to the left.
Yep. And then we add all the y-axis components together, which yields 46.29 newtons J.
So overall, pulling upward.
Exactly. So now we've essentially boiled the whole chaotic system down to just two straight lines, one pulling left, one pulling up.
Okay, tutor, show me the final step on slide 10. Because we have an up force and a left force, but we need one single resultant vector.
Right, we have to reconstruct it. And since our two forces form a perfect right angle, we just use the Pythagorean theorem.
Oh, a squared plus b squared equals c squared.
The classic. We square the x total, square the y total, add them, and take the square root. And that gives us the magnitude of the final resultant vector, which we call r.
And what's the final answer for the magnitude?
It comes out to exactly 71.80 newtons.
Okay, but we still need the direction.
Right, the angle. For that, we use the tangent function, and we find out it's pulling at a 40.14 degree angle into that top left quadrant.
Boom. Problem solved.
The problem solved.
But, the math engine is beautifully precise, I'll give it that. But some students are visual learners.
Very true.
Like, if math is the engine, slide 11 says geometry is the map. What happens if we just, draw the journey instead of calculating it?
That is path 2, the graphical method. And specifically, we look at the polygon method, which is also known as the tail-to-tip method.
Tail to tip. I like the sound of that.
It's very intuitive, and the deck also mentions the parallelogram method. But let's focus on tail-to-tip first, using the sample problem from slide 12.
Oh, the explorer scenario. I really like this one.
Go ahead, read it out.
Okay, so imagine an explorer leaves his hut in the dense jungles of Africa.
Got it.
He walks 40 steps northeast. Then he turns and walks 80 steps at 60 degrees north of west.
Okay.
And finally, he walks 50 steps due south.
So a lot of zigzagging.
Yeah, exactly. So how do we actually plot this journey on a Cartesian plane? Like north, south, east, west.
Well, you start at the origin. You draw your first vector arrow representing the 40 steps northeast.
Okay, drawn.
Now, here's the trick. You literally attach the tail of the second vector to the tip of that first vector.
Oh, so where he stopped is his new starting point.
Exactly. From that tip, you draw the 80 steps pointing north of west,
Right.
and then you do it again. From the tip of the second vector, you attach the tail of the third vector, the 50 steps south.
Wow, okay, so you literally just have a map of his exact path.
You do. And to find the resultant vector, the final answer, you just draw a brand new straight line connecting the very first tail, the origin,
Yeah?
all the way to the very last arrowhead.
The first tail to the last tip.
Exactly. That line is your resultant, R. It shows you his total net displacement from the hut.
Okay, but wait. I'm looking at the slide and I have to push back here.
Uh-oh. What is it?
Well, the slide says we have to reverse the direction of the resultant at the end. It calls it an inverse R.
Ah, yes.
But why would we do that? We just perfectly plotted his path from start to finish.
Mhm.
Why flick the arrow?
This is a classic trick, and it's a huge aha moment for students.
Okay, explain it to me.
Think about what the problem actually asks. It doesn't ask, where did the explorer end up?
Right.
It asks for the displacement needed to return him to his hut.
Oh, wow. Wait, really?
Yes, the R vector we drew shows the path from the hut to where he is now. To get him home, he needs the exact opposite path. Same magnitude, but 180 degrees in the other direction.
That is, wow, okay. That's sneaky, but it makes so much sense. It really reminds you that reading comprehension is just as important as the geometry itself, you know?
Oh, absolutely. If you solve the wrong problem perfectly, you're still wrong.
Very true. And just to briefly touch on slide 13, it gives a nod to the parallelogram method, which is another graphical way to solve these, usually with just two vectors starting from the same point.
Right. It's good to have options depending on what makes visual sense to you.
Yeah, totally. And I should note the slide author signed off by inviting questions to dieslearningstuff@gmail.com or their YouTube channel, Dies Learning Stuff.
Nice of them to offer help.
Definitely. So just summarizing this, think about the immense value you, the listener, just gained here.
It's a lot of power, really.
It is. You now have two proven methods, a mathematical engine and a geometrical map to make sense of complex competing forces. You don't have to just guess where things are going to end up.
No, you can calculate it with absolute certainty. And, I want to leave you with a final thought to mull over, kind of building on this.
Oh, I like where this is going. What is it?
Well, today we learned how to deconstruct physical forces like newtons or directional steps into really manageable horizontal and vertical components.
Right, the X and Y.
Exactly. But what if you applied this framework to the non-physical forces in your life?
Ooh, the non-physical forces. I mean, what does that look like?
Well, think about it. The next time you feel pulled in conflicting directions by, say, your career, your family, and personal goals.
The ultimate tug of war.
Right. Could you map out your competing vectors? Could you isolate your own X and Y components to mathematically find the exact trajectory you need to take to get back to your own hut?
Wow. That is a really profound way to look at it. Just breaking the chaos down into components.
Sometimes you just need to draw the arrows to see where you're really going.
I love that. Well, that wraps up our deep dive for today. Thanks for joining us, and we'll see you next time.